Okay, so Sean introduced me. I'm going to be giving a talk about sodium emissions and fine structure. So our goal is to measure the fine structure splitting of the 3p1/2 and 3p3/2 states in sodium. So what we're going to do is we're going to use a Cerny-Turner monochromator, which is depicted here. We'll take a deeper look into it later. One thing that I want to note about sodium is that sodium is like a hydrogenic system, except it has 10 core electrons, and we'll see how these things ultimately affect the physics. So here's Erwin, and basically why we're doing this, and our motivation for doing this, is that one of the great successes of quantum mechanics, especially early on in the days of the foundations of quantum mechanics, is the predictions of the emission lines of hydrogen, which my partner Tom will talk about on Tuesday. So one thing we kind of want to look into and talk about is how well does this model, do these simple models of hydrogenic systems, apply to sodium, which is an alkali metal and ultimately has 10 core electrons, which kind of mess everything up. But we'll see that, and we'll kind of quantify that. So what we're going to do is we're going to jump into a simple model of a hydrogenic system, add fine structure perturbations, and see kind of how that affects everything and what ultimately that will tell us about sodium. So here's our Hamiltonian, and it just has a Coulomb potential. And what this does is it ultimately gives us solutions that with 3 quantum numbers, we have n, l, and ml. We also have spin, because the electron has spin. But what we do is we get an energy spectrum that's highly degenerate and really only depends on the principal quantum number n. And this is something that you see in hydrogen, and it works fairly well for determining the gross energy levels in the gross energy spectrum. So now, one thing I'd also like to note is that this alpha squared. So we have an alpha squared here. This is the fine structure constant. It's 1 over 137. And it kind of determines the magnitude of the splitting. So just note that. So how well does that equation map to sodium? Well, it doesn't. It's really terrible. If you try to take the 1 over n squared and you try to figure out what's going on in sodium, you're going to get really confused. And the reason you're going to get really confused is those 10 core electrons. It's very simple. So different orbitals with different orbital angular momentums have different shapes, and those different shapes have different average radii. And those different radii affect how much that electron experiences the nuclear charge. So for s orbitals, they penetrate into the core, into this spherically symmetric electron core, and so they experience higher nuclear charge, whereas the p orbitals and the d, they're farther out, so they have higher average radii, and they experience a more hydrogen-like potential level. So yeah, so it doesn't match really well, and the reason is basically core electrons. So these are our measurements, by the way. This is actually the hydrogen that we measured, and this is the sodium that we measured, not just a random graphic. So so now what we can do is we can add a fine structure perturbation to our model. And it will ultimately give us information about the right basis to describe our states, even though it won't tell us much about the magnitude of the fine structure splitting. So what we do is we add 2 terms. I've only shown one. One of the terms is relativistic. It goes like p to the 4th. Actually, both of these terms are really relativistic. The full solution to hydrogen comes from the Dirac equation, which is relativistic, and Schrodinger's equation is not. But what we do is we include the first 2 terms from this expansion of Dirac's equation. And the one that I would like to talk about, the one that's interesting, they're both interesting, but the one that's more interesting is the LS coupling term. Okay, and even though the real motive behind this LS coupling is the expansion of Dirac's equation, we can motivate this semi-classically, and it's very easy to understand semi-classically. We have an electron, and it's orbiting the nucleus. Well, it's a current loop. Current loop creates a magnetic field, and the electron is a magnetic moment. So you have a magnetic moment in a magnetic field. There's a magnetic interaction. And so that kind of motivates this term. Now, if you just use semi-classical motivations and stuff like that, you're off by a factor of 2. which is an interesting factor too that we're not going to talk about. So you get a spectrum, a degeneracy splitting that goes like J. And J is the total angular momentum. So what you do is you couple the orbital angular momentum with the spin angular momentum, and you get a new basis, and the energy splitting goes like this. So now note, in our previous slide, let's go back. We can see it goes like alpha squared, right? That kind of determines the scale of the energy splitting, along with other stuff, but whatever. Now there's an alpha squared in here, in the En, and there's another alpha squared. So 1 over 137 squared, the fine structure splittings are going to be smaller by that factor. And this is what we see. So the 2p states, which previously were degenerate, now the degeneracy splits. J can either take on values of 1/2 or 3/2. And so our whole goal is to measure this splitting. Now, if we just use this formula, we get a prediction of the wave number splitting. Wave number is 1 over the wavelength. And the energy is equal to hc times wave number. So an energy splitting is a wave number splitting. We predict, just from this model, a wave number splitting of 100 inverse meters. Which is not what we observe at all. We observe something that's about 17 times greater. And here's our observation. And once again, it's the core electrons. So let's take a look at the apparatus. Oh, what we want to do is we're going to set out as if we're trying to measure wave number splittings of about 100. And that is going to correspond to a resolution of about 0.1 angstroms at wavelengths of about 4,000 angstroms, which is typical to what we're measuring. But here's our apparatus, and let's kind of step in and see what's going on. We have a lamp, and what the lamp is, it's a discharge lamp. So what we do is we take electrons and we throw them at sodium, and the sodium gets all excited. And usually it's the optical electron. It's that highest energy electron. The sodium, that electron gets all excited, dances with the electromagnetic field, and there's a fountain of photons, and some of them spill out onto this entrance slit and illuminate the entrance slit, and then, which is a rectangle of adjustable size. And light comes from this entrance slit, and this rectangular beam propagates all the way to mirror 1, which is a parabolic mirror. So the light, this beam, comes down, hits mirror 1, and is collimated and sent onto a grating. The grating's job in life is to take a frequency distribution and turns it into an angular distribution. So it takes frequency and angularly disperses it. So it throws red this way and it throws blue this way. And what we can do is we can turn this grating using a nice motor that Charles and I broke and fixed. And you can use this to just kind of like turn and look at different colors. And that's how we're going to get our wavelength data. That's how we're going to look at our peaks. So the grating makes angular dispersion at a frequency. The parabolic mirror turns that angular dispersion into a linear dispersion. And ultimately, what we're going to get is about 350 microns of dispersion per angstrom. So this is the dispersion that we have. Now, our exit slit widths are about 10 microns. So this is about 10 microns. This is about 10 microns. And then you add like a geometrical factor that's involved when you convolute two rectangles together, which is about 3. And what you get is, ultimately, you get about 10 effective slit widths per angstrom, which gives you a resolution of about 0.1 angstroms. So we have about the resolution, kind of, that you need to measure the wave number splitting of about 10. So the light ends up going to the exit slit and it hits a photomultiplier tube. You take your optical signal, turn it into a current signal, you amplify it, you count it, and we get distributions that look like this. So here is this is number of counts, number of photons that are hitting, and this is actually counts per second, so this is count rates. And these error bars are just determined by Poisson statistics. We have our wavelength. This is calibrated. The way we calibrate is we take a look at a mercury spectrum, and we know the mercury emission lines. I mean, smarter people than I have measured these things, so I trust them. And the calibration data points are from NIST. And so this is a typical run for 10 micron entrance and exit slit. With an integration time, the counts are taken. Each point is taken over 500 milliseconds. So we're just changing the angle of the grating, and we're looking at different wavelengths. And what I really want to talk about here is how we determine the center of the peaks that we're looking at. So what we're doing is we actually just went in each file, and maybe a little arbitrary, but we selected a region of interest. We calculated the first and second cumulant, the mean and the standard deviation. And that gives us this value, that your mean and your peak width. But there's also the uncertainty in the determination of the mean, which is just propagated from Poisson statistics. And then there's the uncertainty in the calibration. And this kind of dominates all other errors. It is the weakest part in our experimental technique is the calibration. So the error from this is about 1 angstrom, whereas the peak width is 0.07, and the uncertainty in the determination of the mean is ridiculously small, very negligible. Okay, so one thing that we kind of wanted to talk about, one thing we wanted to investigate is, or at least what we put into the errors of the calibration, was how does the instrument physics, how do the slit widths ultimately broaden our distribution? So this kind of takes into, this is like, what is our spectral resolution? What is the instrument capable of? So what we did is we took a laser. We took a helium neon laser, which is expected to be extremely sharp in frequency space. And then we broadened the beam and diffused it and sent it through the apparatus, hoping to have some frequency delta function going into the apparatus. And then we took a look at the shape, the resulting shape that we saw. And what you expect to see is a rectangle convolved with another rectangle. The image of the entrance slit onto the exit slit, you convolve them. And so you expect to see something like a trapezoid. And this is approximately trapezoidal. And what we wanted to ultimately find is a figure for the uncertainty in the determination of the mean. So what we did is we took the width associated with 10% deviation from the peak of our laser test, which is a frequency delta function approximately. And we get a width of 0.1 angstroms, which that went into the uncertainty in the calibration, and that's ultimately what yields the 1.6 angstroms. So by the way, this is just a little aside. The calibration is very linear, but we also add a quadratic term to the mix, and it does a nice job of cleaning up the calibration. Probably the most cogent thing to do is just linearly interpolate and extrapolate from the calibration points. But this is our result. We measured 10 couplets, all of the 2p splitting states. So here's your 2p 3 halves, 2p 1 half, and you have a whole bunch of different states transitioning to or from this couplet. And so we ultimately get 9 data points and lots of colors. And so what we did is we can match these transitions. We can match these states, transition between states, to the spectrum that we've measured. And one thing that's really interesting, some interesting physics, is you never see a transition between a p state and a p state. It's always between d and p, or an ns and p. And the reason being is photons have angular momentum. And so when a photon is emitted, carries off some angular momentum, you need to have a change in the orbital angular momentum of the system. So that's why you see these terms that tell you the orbital angular momentum. It's always S and Ds and S and Ds. So that's ultimately our results. And what we could do is we can compute the splittings in the wave numbers from the wavelengths of each of these here. So and that's what we do. And these are our results. So this is your expected value for the wave number splitting of the 2p states. And so the way you go about getting this is, well, one, you can measure it experimentally, and this value is from NIST. But another way that you can do it is you can do numerical computations of alkali systems, which have no closed-form analytical solutions. So we see the data falls fairly close to the expected value, and we can calculate the mean. And we can get 1731.9 plus or minus 8.8 systematic, which is dominated by calibration error, and then 12.1 statistical fluctuations in the points that I just showed you. This is fairly close to the accepted measured value by NIST, which is 1719 inverse meters. It is quite a bit off from the predicted value just using Schrödinger's equation with fine structure perturbation. And then one final thing that we can kind of look at is maybe does this formula at least kind of work for the scaling with n, with the dependence on n? And it kind of does. So what we did is we measured another couplet, which is the 4p1 half state. We only got one data point for it, so it's not terribly reliable. But we have 572 as the splitting, and this is approximately, it's off by like a factor of 1.3 or something like that. 3 over 4 cubed, which, so this goes approximately like n cubed. Ultimately, we detected these emissions. We connected them to transition states. We looked at the selection rules, which is, you know, the delta L equals 1. We determined the wave number, and we're plagued by errors in the calibration. I'd just like to thank the technical staff and Tom. Thanks, Charles, for being a great guy and helping me fix the monochrometer, and Sean and Cameron for grading everything, and Jim. Yeah. Thank you.